Today, we're going to continue to take a systems perspective of things and look at how to evaluate environmental impacts of industrial processes using life cycle assessment. Our pulp mill is an interconnected system of processes: wood handling, pulp cooking, chemical recovery, and energy generation. Each of these processes requires energy and material inputs and produces both useful outputs and wastes. Yet, the pulp mill is itself part of a larger system. The pulp requires wood and chemicals and fuels, each of which has to be produced and transported to the mill. After the pulp is made, it may be finished into paper or newsprint or cardboard, which is then transported, used, and discarded. This larger system is what we're interested in today. Life cycle assessment is not only interested in what happens within the factory gates, but everything associated with pulp production, regardless of when or where it takes place. As defined in the ISO standard 14040, life cycle assessment, or LCA, is a compilation and evaluation of the inputs and outputs and the potential environmental impacts of a product system throughout its life cycle. By using LCA, we can make more informed decisions that work towards sustainable production and consumption. In our case, while some environmental impacts occur at the pulp mill, such as greenhouse gas emissions from fuel combustion, many will occur elsewhere. In the forest where the timber is grown and logged, in the chemical plant where sodium hydroxide is made, in the quarry where limestone is mined, in the power plant supplying electricity to all these places, on the roads and rails and waters traveled by trucks and trains and ships, carrying inputs to our mill and carrying our pulp and paper products to the world, and also in the incinerator or landfill or recycling plant where our pulp products eventually end up. In our increasingly globalized world, our impacts and our product systems are also increasingly globalized. But what exactly is a product system in life cycle assessment? The most important thing to know about a product system is that it is not defined by a product, but by the function. What do we use the product for? We produce pulp to make paper products, but those paper products serve a variety of functions: conveying information, maintaining hygiene, protecting goods in transport. When we compare different product systems in life cycle assessment, we don't compare based on the amount of product produced, but on the amount of function provided. That said, product systems can typically be divided into three parts. There is the center of the system, which is often the site where the product is produced. In our case, this would be the pulp mill itself. All processes related to the inputs to the pulp mill are part of the upstream supply system. This includes material and energy supply chains, transport, and the supply chains of the supply chains, all the way back until the raw materials such as minerals, fuels, or biomass were extracted from the environment. On the other side is the downstream system. This includes any conversion of the pulp to other products, the transporting use, the disposal of products and byproducts, as well as the processing of wastes. Importantly, life cycle assessment does not put a time limit on when these processes or their associated impacts occur, but follow them cradle to grave, including all processes and impacts from the initial extraction of resources from the environment to the final fate of all products, material, waste, and emissions. Now that we know what our system is, what data do we need to perform a life cycle assessment? We need to inventory the inputs and outputs of each process in the system. LCA divides these inputs and outputs into two categories: economic flows and environmental flows. Economic flows are essentially any input or output that humans find valuable enough to use. These include goods, materials, energies, and services. Environmental flows are those that are extracted from or emitted to the environment, such as in the air, water, or soil. An inventory of flows for a single process can look something like this. And an inventory of flows for a system can look like this. There's usually quite a lot of them. While the ideal life cycle assessment was use direct measurement data for all processes in the system, that is rarely feasible. So typically, a foreground system is defined where data is collected as directly as possible. For example, pulp production, energy generation, and paper recycling might constitute the foreground in a pulp system, as these might be the processes that the pulp mill has the greatest control over. Processes not in the foreground system are in the background system, and the data from these often come from more generic sources, such as lifecycle inventory databases or industry data. A large background system reduces the effort involved in the life cycle assessment, but also reduces the potential specificity and accuracy. However, at the end of the day, we are not really interested in long lists of inputs and outputs. We are interested in the environmental impacts they cause. You've probably heard of impacts such as global warming, acidification, or human toxicity. These are called midpoint impacts because they represent measurable physical phenomena, but don't actually tell us what we really want to know. Generally, the reason we care about these impacts is because they harm us. They harm our health, they harm the ecosystems in which we live, and they harm our ability to provide for ourselves in the future. These endpoint categories represent what, in the end, we care about. But unlike global warming or eutrophication, they're much harder to estimate and require value judgments of how to weigh specific impacts against each other. So midpoint indicators are much more common. Life cycle assessment relates the inventory of flows to these impact categories in a sorting process called classification. Classification labels environmental flows with the environmental impacts they contribute to. A single environmental control may contribute to multiple impact categories, and a single midpoint category might contribute to multiple endpoint categories. However, not all environmental flows are equally impactful for a given category. For example, methane has 28 times the 100-year global warming potential of carbon dioxide. This means that for every kilogram of methane emitted over the course of a century, it will heat up the atmosphere as much as if 28 kilograms of carbon dioxide were emitted. Therefore, life cycle assessment uses a process called characterization to factor environmental flows into a single standardized unit. Characterization factors relate all the flows in a given impact category to the impact of a single representative flow. For example, global warming is typically characterized relative to carbon dioxide, usually on a 100-year timescale. Timescale is important. As we noted, methane has 28 times the global warming potential of carbon dioxide on a 100-year timescale, but 86 times on a 20-year timescale. In contrast, sulfur hexafluoride has a global warming potential 23,500 times that of carbon dioxide on a 100-year scale, but only 17,500 on a 20-year scale. Different greenhouse gases, like many chemicals released into the environment, behave differently over different periods of time. By the way, you don't have to worry about doing all this math by hand. Software and databases exist for that. We're linked to some of those in the extra information for this module. The process for conducting life cycle assessment, while still a field of active development, has standardized procedures, such as in ISO 14040 and 14044. Today, we talked a little about the goal and scope definition, which includes defining the function and system boundaries, the process of collecting data for the inventory analysis, and two of the fundamental steps of impact assessment. We did not talk about interpretation, which is how you explore and assess the results of the other steps in the life cycle assessment. But you'll get to explore all of these a bit more in this week's assignment.